what we'll be going over today is a really important result in finite group theory, and it tells us a lot about the structure of a group just based on its order. So we have a group G with order n, and n equals p to the e times m, where p is prime and m is co-prime to b, which is to say e is the greatest it could be, such that m is an integer. So the first Salo theorem is simply that there is a subgroup of G with order p to the e. So for example, for any group of order 12, that means that we're going to have, if we take p equals 2, then e equals 2 and m equals 3. So, and if we take p equals 3, then e equals 1 and m equals 4. So any group of order 12 will have a subgroup of order 4 and a subgroup of order 3. And there's no way around this. Any group will have this. So that's already quite restrictive on what the structure of the group can be. Right? And we'll see some examples of this later on. An immediate consequence of this is that corollary, I'll add the numbers that they give you in the book for clarity too. This is theorem 4.2, and this is corollary 4.3. But this is called the, this theorem 4.2, I labeled it as theorem 1 because it's called the first Salo theorem. And if you look it up, that's what you'll find it called. Salo theorem 1, Salo theorem 2, Salo theorem 3. So if we have so if p divides the order G, p for p prime, then there is some an element of the group with order p. And we can prove this. I will prove the Salo theorem itself later, but I'll defer that until we've seen some examples and kind of get an intuition for how they can be used. So we just take, obviously we're going to take H of order p to the e, that subgroup. And so take any element of H. E is greater than or equal to 1 if p divides G. So take any element of H with order greater than 1, right? Then in the order of H, it has to divide p to the e. So the only divisors of p to the e are either prime powers, p to the r, And then we just have to take let x equal h to the p to the r minus 1. And this, the order of this, the order of x, will be, the order of x will be p. Because the order of h is r, and so if you raise this to the power of p, obviously the exponents will multiply and we'll get p to the r, and it will be 1. Any questions so far? Nope. Okay. So again, like if we have a group of order 12, this immediately means that there's an element of order 4 and an element of order 3. So like there is no way, for example, to have a group with all elements of or if a group has all elements with order 2, like x squared equals the identity for no matter what, then the order of that group has to be a power of 2, right? Because otherwise we'd have some, or it has to be infinite if there's a finite group. Because otherwise we'd have some element with a non, it's the order of some other prime. So actually, if we look at groups of order 6, right, there's actually only 2 distinct groups of order 6 up to isomorphism. So if we say that the order G is equal to 6, sorry, did I think Discord lagged there for a second? Okay. Yes, that's right. Okay. So yes, so we have a group of order 6, and then we can take, by that corollary, we can take some x and y in G, such that x has order 3 and y has order 2. And so we have x to 0, y to 0, x to the 1, y to 0, x squared, y to 0, x to the 1, 0, y to the 1, y to the 1, x squared, y to the 1, and these will be our 6 elements. Now, in particular, we have xy is one of the elements of the group. And we can't have we have yx is one of the elements of the group, and we can't have yx equal to, well, it can't be equal to, we try to identify which of these 6 elements of the group it's equal to, right? So it can't be y, because then x would be the identity, and similarly, it can't be x, nor can it be x squared, because then y would equal x. That certainly can't be the identity itself. So then we have, because the inverse of an element would be has the same order. So either yx equals xy, or yx equals x squared y. And in this case, the group is isomorphic to the cyclic group of order 6. And in this case, the group is isomorphic to the dihedral group of order 6, which is to say the group of symmetries of a triangle. So these two isomorphism groups, they're the only possible isomorphism groups for order 6. Any questions about this? Nope. Okay. So we can see that this is quite powerful, the tools that we have here, that the Silo theorems give us. Like already, like there's only, of all the possible multiplication tables, we know that there's only really 2 fundamentally distinct ones that are valid for groups when it comes to 6 elements. Now, if we have a subgroup H of G such that the order of H is P to the E, so it's one of those groups whose existence is implied by the first Silo theorem. We have, we call H a Silo subgroup. And in particular, we call this one a Silo P subgroup. Of G. A Silo subgroup is always relative to some other group G, obviously. So, the second Silo theorem is let K be a subgroup of G such that P divides the order of K, and let H be a Silo P subgroup of G, which is to say it has order P to the E. Then there is some, either H or some conjugate of it. So for some G, we have an H prime such that the intersection of K and H prime is itself a silo P subgroup, or a silo subgroup. Of K. So to prove this, yes, okay. Have we shown? Sorry, I think there's a lemma here that we don't encounter until there, so I'll defer the proof again. Just reorder that. Okay, so yes, I'll talk about the proof of this in a little bit, until after we've proven the first one. But again, an immediate consequence of this is that well, two things. If K is a subgroup of G, and K is a P group, then K is contained within a silo P subgroup of G. Sorry, to be clear about theorem 2, I think I misspoke and said, when I was writing this out, I said that K intersect H prime is a silo P subgroup of K. It's just a silo subgroup, so it might be of some other order. Oh wait, no, never mind. Just forget what I just said. No, it has to be a P group, of course. And also, and this one's important, other corollary is the silo P subgroups of G are all conjugate. So we might have several silo P subgroups, right? Like if we have a group of order 12, then we might have many subgroups of order 4, which would be the two subgroups, the silo 2 subgroups of the group. But we know that all of them are conjugate. Right. So so for the first one, I'll write them to the side actually. If so right. So we have so the silo subgroup of K is just K itself. Meaning that by this theorem, we have some conjugate of H such that K intersect H prime is a silo subgroup of K, but that just means in this case that it's K itself. So there is some conjugate of H such that which itself must be a silo P subgroup being the same order, such that K is K intersect H equals K. Which obviously means that K is contained within H. And for the second one, if K and H are silo subgroups, then by this first part, there is some conjugate H prime of H that contains K, but the order of the conjugate and the order of K are the same because they're both BP to the E. So that means K and H are conjugates of each other. Questions so far about any of this? Okay. In that case, theorem 3, cap it off. So this is the last silo theorem. Let S be the number of silo P subgroups so of G as usual. I should probably say explicitly in all this I'm using the same notation where P to the E times M is equal to the order G and M is co-prime with P. So if S is a number of silo P subgroups, then S divides M, and S is 1 mod P. So again, let's take a look at like the groups of a certain order this time. Let's say order 15. Again, I'll prove the three cell theorems at the end. So say you have a group G of order 15. The number of silo 3 subgroups, now looking at theorem 3, the number of 3 subgroups I guess it should call them silo 3 subgroups. But silo 3 subgroups are obviously those of order 3 in this case. So we have, it divides 5. Sorry. S3, the number of silo 3 subgroups, divides 5. And it's congruent to 1 mod 3. Right? That's exactly this notation. Recall that, sorry, I used M here without. Right, now recall that we saying G equals P to the E times M. Right, so the M here is the leftover after we take the power of P out of the order G. Right, so this is what the cell third theorem tells us, and obviously this means that S3 equals 1, because there's only 2 factors of 5, and 5 itself is not equal to 1 mod 3, so it has to be 1. And again, we have, so let's call H that silo 3 subgroup. And if we do it for, same thing for order 5, we get S5 divides 3, and S5 is 1 mod 5. And this has the exact same consequence, that S5 equals 1. So call K the subgroup of G, where K has order 5. And any subgroup with no conjugates is normal, because that's part of what it means to be a normal subgroup, is that you can conjugate the group and it will be the same group. So if there's only one group of a given size, obviously if you conjugate it, you have to end up with the same group. So both of these are normal. So their intersection is the identity, or rather, not the identity, it's the trivial group, what I meant to say, and containing only the identity. And K times H is a subgroup of order at least 6, but there's only one of those. So it has to have, it has to be G itself. And now we apply, I'm not sure, does this book call it the second isomorphism theorem? Anyway, yes, so recall, this is a really important group theory theorem, is that when S and N are both subgroups of G, and N is a normal subgroup, we have these two quotient groups are isomorphic. So in this case, that tells us that G is isomorphic straightforward application. It's the direct product of H and K. And H is order 3, which means it has to be isomorphic to C3. And K is order 5, which means it has to be isomorphic to C5. So overall, this group, we know the exact isomorphism class of G, and it's going to be C15. So the only group of order 15 is cyclic. Or rather, any group of order 15 is cyclic, and they're all isomorphic to each other. Questions about this? Okay. Well, let's do the same thing for order 21. So if G has order 21, so notice, by the way, like in both these cases, here 15 is 3 times 5, and here this one 21 is 3 times 7. In both of these cases, we have a small number of products of G, and that's generally when the Salo theorems are the most useful. If you have too many products, too many distinct prime factors, the Salo theorems become less and less useful because there's it becomes less and less tractable to actually get some meaningful information out of it. But for products of just a couple prime numbers like this, we have it pretty easy. So this one, there's going to be 2 isomorphism classes. Either G is isomorphic to the cyclic group of order 21, or it's generated by 2 elements, X and Y, such that X is order 7, and Y has order 3. And yx equals x squared y. Hopefully this group generator notation makes sense. Not 100% sure if you covered that or not, but just means that we take the largest group we can such that it satisfies these conditions on x and y and is generated by x and y. And that will be the other option compared to the cyclic one. So again, the Silo 7 group in this case, we have S7 S7 divides 3, and S7 equals 1 mod 7, or is congruent to 1 mod 7. So S7 equals 1, and there's a single normal Silo 7 subgroup of order 7, or G. So let's call this group K, which is a normal subgroup of G with order 7. And because it has, sorry, the mic just fell. Can you hear me? Great. So because it has order 7, because 7 is a prime number, obviously it's going to be cyclic, so it's going to have some generator x. So let's say x, and let's call so if we apply this, if we try to apply the third theorem to S3, we get S3 divides 7, and S3 is 1 mod 3. And in this case, that doesn't actually narrow it down to just one option. We could have a single, unique Silo 3 subgroup, which is normal, or we could have 7 distinct ones, or at least we can't rule out the possibility that we have some distinct ones based on the theorem. But in any event, let's find an element. We know that we know by the first theorem, or by its corollary rather, recall that we have an element y of order 3 in G, and y will generate one of these Silo 3 subgroups, or the Silo 3 subgroup if there's only one. So we have x is as an element of order 7, and y is an element of order 3, generating this 7 and 3 subgroups respectively. So x is 7. Keep writing that. X is 7 equals y to 3 equals 1. And y x y to the minus 1. This is because k is normal. This is in k, but k is generated by x. So this means that it's equal to x to the I for some I between 0 and 6. Now, since y to the 3 equals 1, if we say that x is y to the 3, x, y to the minus 3, these are both the identity, then we can apply this formula a couple times. That's y squared x to the I, y squared now applying it I times, that's y x y, sorry, y x to I squared y, and applying it I squared times, that's x to the I cubed. So x equals x to the I cubed, which means I cubed is congruent to 1 modulo the order of x, which is 7. This leaves the possibilities I is 1, 2, and 4. So remember, x to the I is y x to the y minus 1. And it only matters, we only care about modulo 7, so we'll say it's less than 7. So now we can do casework on this. So if I equals 1, then this, I equals 1, then right, so you can hear me? Oh. Sorry, I said that the previous, if I equals 1, this is the same method we can use as the previous case where the group was of order 15. We can apply the second isomorphism theorem and show that G is the direct product of G is a direct product of C3 and C7, or it's isomorphic to it, and is thus cyclic itself. And again, this is just the same logic that we had. The full logic was what we did in the case of the group of order 15. So, case 2, I equals 2. So in this case, y x, y to the minus 1 equals x squared. And this is the case that that leaves us with the other possibility listed up here. So in this case, we have x is 7 equals y is 3 equals 1, and yx equals x squared y. Right? We can rewrite this as yx equals x squared y. And in the case of I equals 3, we have yx to y minus 1 equals x to the 4. I said I equals 3. I equals 4, of course. That's what I meant. In this case, actually, if we let y prime equal y squared, recall that y is a generator of a group of order 3. So y squared will be the other non-identity elements in that group, and it will also be a generator of that group. Meaning that y equals y prime squared. And then y prime squared x y prime to negative 2 equals x to the 4. Which means whatever. Right. Which means that y prime x y prime is negative 1. Oh yes, sorry. Right. So y squared x y negative 2 equals, based on this, sorry, forget that. I was confusing myself with my notation. Y squared x y to negative 2 is y x to the 4. Y to negative 1 is x to 16. Just by applying this formula 4 times. Which is x squared. And this y squared xy to negative 2, that's y prime x y prime to negative 1, using this definition. But in this case, we have y prime x y prime to negative 1 equals x squared, where y prime is a generator of a silo 3 subgroup. And that's actually this previous case, where I equals 2. So we've reduced this to the previous case. And there's only really 2 cases. And that's the proof. There can be no other isomorphism classes for order 21 other than these two. Any questions about this? So, proofs of the theorems. So we haven't proven them yet, which I'll rectify now. So, just theorem 1 is that so in all the below, we're going to let G be a group of order p to the e times m, such that p and m are coprime. And then theorem 1 is that there is some h, some subgroup h of G with order p to the e. So, how do we prove this? So let S be the set of all subsets of G with cardinality p to the e. So not subgroups, subsets. And one of these subsets is the subgroup that we're looking for. We'll show it indirectly using group actions on the subsets of this. So first thing to note is that the size of S is n choose p to the e. Obviously, oh yes. We call the order itself n of G. So obviously this is pretty much the definition of choose. And also the order of S is not divisible by P. So this one's a little so, but if you write this out as a big product, it's not too difficult to see, and it's a good exercise to reason it out. But the number of times that p divides the numerator and the number of times that p divides the denominator of this fraction is the same. So there's the same number of there's the same amount of times p divides each is the same. It balances out in the end. There's one multiple of p to the e in each case. There's the same number of multiples of p to the e minus 1, same number of multiples of p to the e minus 2, and so on. And so that means that P does not divide the size of S. Now, so we can, in my last talk on 6.3, I think it was, we talked about using group actions and extending that from the elements of a set to the to subsets of the set. And we're going to do that here. So we're going to use the group action of left multiplication, the operation of left multiplication, acting on so the action acting on the elements of S. So the subsets of G itself. We're going to let the elements of G act on the subsets of G. And so if we break up S into orbits, it's orbits, right? We can just, those form a partition, so we can say that S is the sum, the size of S is the sum of the size of O, where for all orbits O. And so it can't be the case that all of these orbits are divisible by the size of all these orbits is divisible by P, because then P would divide the order of S, which it doesn't, or the cardinality of S, which it doesn't. So let U be an element of S such that the orbit of U, the notation we use for this is just O of U, P does not divide the orbit of U. So U is, we know that not all orbits can have cardinality multiple of P, because the total sum doesn't have cardinality multiple of P. So we just take one of those orbits and we let U be one of the elements that generates that orbit. One of the elements of S, which is to say one of the subsets of G. So now, from the previous lecture, we had a proposition which said that the orbit of the stabilizer of U for this group action of left multiplication divides the order of U itself. So say the order of the stabilizer for the operation of left multiplication divides the order of U. And this states the stabilizer of U, that's going to be our subgroup. This will be the P subgroup that we're looking for in the end. So we have stabilizer of U times the orbit of U is G by the counting formula. And we have this is not divisible by P. So this not divisible by P. I won't write out there, but the point is that because this product equals P to the EM, we must have that P to the E divides this the order of the stabilizer. But because these are groups of size P to the E, this order of the stabilizer must be a power of P itself, meaning that the size of the stabilizer is P to the E. And that's our group. Because we want to find a subgroup of order P to the E, and this is one. Any questions? Mm-hmm. No. So we have the step here, right, with the orbits, where we say that the size of S is equal to the sum of the orbits, and we have to find an orbit that such that P doesn't divide the size of the orbit, right? So we're limited in our choice by that. U can be any one of the sets that has an orbit that doesn't have size, or that is not a multiple of P. Yes. Okay. If no other questions, then we'll move on to the second one. Which is, let me find the statement. So, again, let's K be a subgroup of G. With the order of K, with P dividing the order of K. And let H be a silo subgroup of G. So the order of H is P to the E. Then for some G, we have a conjugate of H prime, such that K intersects H prime is a silo subgroup of K. So which is to say, we can find the shallow subgroups of a group by intersecting that group with one of the shallow subgroups of the greater group itself. It's kind of the notion. So the proof here is so in this case, let S be the set of left cosets of H and G. So again, we're going to that G acts on S. So if we okay, so let's restrict the operation of G into K and decompose S into K orbits. So now the order of S is coprime to P. So there is some K orbit O such that P does not divide O. K being this subset of G, or the subgroup of G from the theorem statement. Such that P does not divide O. And that let's say it's the K orbit of the element A times S. And now let H prime be the stabilizer of AS. Then the stabilizer. So for the entire group operation. This is the stabilizer. Then the stabilizer restricted to K of AS is going to be H prime intersect K. So it'll just be the elements of the greater stabilizer that are in K. And we also have that the index of K in the stabilizer will be the size of the orbit. Which is coprime to P. And H prime, because it's a conjugate of H, it's a P group. So the intersection H prime, no, this is coprime, not divided, I should say. So H prime intersect with K is also a P group. And it must be, therefore, a silo subgroup of K. Which is what we want to prove. That for some conjugate of H, K intersect H prime will be some subgroup of K. Questions? Oh wait, sorry. I think I skipped ahead in my notes there for that last proof. I just realized. There's a couple things we need to note there. So G operates transitively on S, right? The set of cosets. So there's only one single orbit. And H would be the stabilizer of H. The coset, well, H is one of the cosets, so H will be the stabilizer of that. And so the stabilizer, if we let S equal one H, the coset there, then H stabilizes this. And then the stabilizer of A times S will be AH to A minus 1. It will be the conjugate of that. Or 1 equals. And that's where this comes from in the proof. So S, so O is the orbit. When I said O is the orbit of AS, and then H prime equals AH prime H minus 1 is the stabilizer of AS, which is in G, to be clear. This is what I was referring to. Sorry about that, I skipped ahead. So then after that, with that setup, just to reiterate, we decomposed S into K orbits, and then one of the K orbits had to have order prime to P, since the order of S itself was co-prime to P. And then we let AS be the element that O is the orbit of, and then where S is H, really, so it's AH is the element that O is the orbit of. H has a coset. Then the stabilizer, that is AH to the A minus 1. And then we compute the stabilizer restricted to K and the index. And from the orders of that, take the intersection, and that has to be a Silo subgroup. Okay, in that case, I really will move on to the third cell theorem now. So, to reiterate, we say if S is a number of Silo P subgroups, then S divides M. Remember that we say the order G is N is P to the EM. So this is the M here. S divides M, and S is 1 mod P. I think that's correct. Yeah, that is. Okay. So, so recall that all of the Silo subgroups of G are conjugate to each other, right? So let's say let H be a Silo subgroup. And let N be the normalizer of H. So the largest subgroup of G where H is normal. Then the number of conjugates of H will be the index of N and G, which is S. And this divides, because H is obviously H is a subgroup of its own normalizer. So this will divide the index of H and G, which is M. So that's one out of the way. S is S is a multiple of M. Or sorry, M is a multiple of S. So all that remains is to show that S is 1 modulo P. Now, to show this, we have a set of the silo subgroups all of which are conjugate to each other. So we can let H act on this set H, which we'll call H1. So we let H act on this set under the operation of conjugation, which will be closed by the second, or by one of the corollaries rather, that follows from the second set of theorems. So the orbits of the set under that operation, an orbit of the set so the operation is conjugation by H. So an orbit of the set under what circumstances will it have has a single element H sub I, if and only if H is contained in the normalizer of H sub I. Meaning, because all of them are conjugate, that H equals HI. So there's only one H orbit of order 1, which is H itself. And any other orbit, it has to have an order that divides H, and H is a silo P subgroup. So all of these other orbits will have an order divisible by P. And the counting formula is that the order of S is the sum of the orbits. Sum of this. And so every orbit O has an order that's a multiple of P, except for a single one, which is H by itself. Which obviously means that this is congruent to 1 mod P. And that's the last one. Questions about that?